Hello, class. Okay, so just part of our review, gonna just do some problems. So I picked a problem out of the book where I've drawn the picture here, where we have in this region below this plane here, the electric field is 0. So we're going to fire this proton into this region with a downward electric field that has a magnitude of 720 newtons per coulomb. Its initial velocity is 9.55 kilometers per second. And we want to hit a target that is 1.27 millimeters away. So the distance from where it enters to where it comes back down and hits its target is 1.27 millimeters. And what we want to find is the angle that we can aim this, have it enter this region with the electric field so that we'll hit the target. Or we want to find either the angle or angles. So that's our goal. Again, this particle is a proton. So the mass of a proton and the charge are also needed, so I'll write those down. Okay, so this is our plan. We want to find the angle or angles that'll get us to the target. So let's say that the proton enters. Let's call that x equals 0, and then it's going to hit this plane at x equals r. So this could be, like this plane could be one plate of a capacitor with the other one up here, so that we create a constant electric field in this region. This problem is from chapter 22, so we haven't gotten to capacitors yet in the book, but now we know how we could actually create that electric field. And maybe there's a little hole in it where we can shoot this proton at a very high speed, have it curl around and hit the plate at a given location. So to start with, we're describing the motion of this proton. And so we're using just F equals ma, Newtonian mechanics here. It's moving slow enough that we can do that. And there's actually two forces acting on this proton. The electric force and the gravitational force. So remember, the electric force the magnitude of the electric force is the charge times the electric field. And the direction, because a proton is a positive charge, the direction is always going to be in the direction of the electric field, which is downwards. And, of course, the gravitational force is mg. And I want to let's calculate these magnitudes in advance. Because, they're both pointing in the same direction. And let's calculate their magnitudes. That'll actually make our lives a little bit easier. The electric force is QE. So we have, charge on a proton is just the elementary charge E. 1.6 times 10 to the minus 19th coulombs. And the electric field is 720 newtons per coulomb. So, just, here, let's see this. And it's 72 times 16. It's the same thing. This is 1152 times 10 to the minus 19 newtons. So I'm going to divide by 1,000. We have roughly 1.15 5 times 10 to the minus 16 newtons. So that's the electric force on this proton in this region. And now let's calculate the gravitational force, just mg. So we have 1.67 times 10 to the minus 27 kilograms times g, 9.8 meters per second squared. So this is going to be roughly 1.6 times 10 to the minus 26 newtons. If we just multiply this by 10, it would be like 1.67 times 10 to the minus 26. And by comparing these two numbers, we can see very easily if we get the same exponent, we could write this as the gravitational force, point like 0.0000. And so, if we add this to this number, this is completely insignificant. So we can ignore gravity in this problem. The gravitational force is so weak compared to the electrical force that we would need to go to like 10 significant figures to even notice it. And so we're just going to consider this particle in a gravitational free zone. So let's erase gravity. It's not a factor in this problem. Okay, so now this is essentially just a kinematics problem. We have a vertical force downwards. So let's describe the path of the particle. So in the x direction, there's no force in the x direction. So the initial velocity makes an angle theta with respect to the horizontal direction. And so the initial velocity in the x direction is v0 cosine theta. And because there's no acceleration, then it's just, the position is just that constant velocity times t. Now, let me write this off to the side. Here, I'm going to write this first, actually. Let's look at the acceleration in the y direction. That'd be the net force in the y direction, which is QE divided by the mass. And this is, of course, just the magnitude of the acceleration. We know it's directed downwards, but the magnitude is QE over m. So now let's look at kinematics. The x-coordinate is just v0 cosine theta times t, and the y component we have the initial velocity in the y direction is v naught sine of theta, and then we have that acceleration term minus 1/2 at squared. And we can plug in QE over m for AY. We know all these values. Let's just think of AY as a number, just like V naught sine of theta is a number. And so, looking at this problem, if you remember back in kinematics, when you fired a projectile at an angle above the horizontal, you derived a range equation, where if the projectile is going to land at the same level that it was fired from, and this is essentially the same thing, except because we have a constant downward force, just like in that projectile problem, we have a constant downward force of gravity. Here we have a constant acceleration. The only difference is the value of the acceleration is different in this case. It's a lot greater in this case. But let's see the best way to go about just, we want to find this angle. So, I was thinking maybe we could do this in pieces. Like, let's just look at this point where we know the x-coordinate and we know v naught, but we don't know theta. So we're going to have to combine these two equations. We're essentially going to have to do, kind of rederive the range equation just with a different acceleration. So here's our basic set of equations. And let's look at this point. Let's label this point B. Or here, let's label it point A. We could say point that enters as A, but we have no reason to label that. So at point A, what we have is R. The x-coordinate is R. And then we have V naught cosine theta times TA. TA is the time that it's going to take to hit this point again. And the y-coordinate is 0. So we have, we just plug in 0 for the y-coordinate, and for t, we're talking about a particular time now. So instead of just t as a variable, it's a particular time. And so our solution, I think our goal is let's divide this the second equation by TA. Now again, you always want to, that should always kind of at least make you question yourself when you're dividing by a variable, because sometimes a variable can be 0 when you don't realize it. So you always want to be careful about that. But this time, this is a particular time when the target is going to hit the ground, or this plane, whatever it is. So it enters at t equals 0, and then it's going to land at some later time, so this isn't 0. So let's actually multiply by 2 to get rid of the fraction and divide by TA. So here we have, for the second equation, we have 0 equals 2 v naught sine of theta minus ay TA. And now we want to solve for TA and plug that in here. So let's solve for TA. So essentially all we're doing here is rederiving the range equation, where the acceleration in the y direction is no longer g. It's given by this, but we're just going through the steps. So now if we plug this into R, we have v naught cosine theta times TA, which is 2 v naught sine theta, divided by ay, which is v naught squared. And then we have 2 sine of theta cosine theta, which is sine of 2 theta. And then we divide, sorry, I'm thinking range equation here. So let's write our final result on the board. I'm going to plug in for ay, everything here. So we have R equals v naught squared. I'm going to write it this way. Okay, so yeah, we have QE, but Q is E because it's a proton. So we have V naught squared sine 2 theta divided by little e, big E, divided by m, so we put m back on top. So this is basically the range equation for this problem, where we just replace G with that. And we want to find out what angle we have to launch that. And you might suspect there's two angles. Because if we have a very low angle, yeah, the velocity is the same in every case. So it's moving very quickly to the right. You think it's going to travel a long distance. However, the y component of the velocity is small, and so it's not going to be in the air for very long before it hits the ground again, or whatever this plane is. And so this is moving very quickly in the x direction, but it's not going to be moving in the x direction for very long. And so, yeah, that might be, we might have a very low angle that's going to hit the target. And then if we increase the angle, we'll overshoot the target. But if we make it a very large angle, you know, again, if it's a steep angle, then it's going to be traveling for a long time, but the x component of velocity is going to be very small, and so we should probably expect two answers to this question. Two angles that will hit our target. And we have to solve for those. So I'm going to erase the board. We have our equation here. We just want to basically rewrite it to solve for theta. So, yeah, let's clear as much space as we can. And then let's solve this equation for sine of 2 theta. So we have little e times big E times r divided by m v naught squared. Now, very important, this quantity that we're multiplying, when we plug in the units, we should just get a number. Sine of theta should always just give us a number, not something with units. So, yeah, let's figure out what number we're dealing with here. And I'm going to have a feeling this is going to take some room. So, also we should note that this number that we come up with should be less than 1. Because, sine of x, whatever x is, that oscillates between -1 and 1. And so if we get sine of 2 theta equals 1.5, then something has gone wrong, and we can't do it. So let's plug in the numbers, and of course it should be a positive number because we have a positive angle here. So let's figure this out. We should get something between 0 and 1, just a dimensionless number. Let's see what happens. So we have 1.6 over 10 to the 19th coulombs. The electric field is 720 newtons per coulomb. So we've got this. R is 1.27 millimeters. And let's divide by just 1. Because of mass, we have 1.67 over 10 to the 27th kilograms. Or 1.67 kilograms over 10 to the 27. And now we have 9.55 kilometers per second squared. Now, out of room here, it's actually not as bad as it looks, though. So what I'm going to do is I'm going to erase these. I'll put these numbers over here. I think we might actually be able to fit what we need. I just free up this room. So first, let's get rid of the prefixes like the milli and the kilo. So we can say 1,000 millimeters is 1 meter. And the kilometers, we want to get rid of that. We can say 1 kilometer is 1,000 meters. And we square that conversion factor. So now let's look at the units and see what we have. I'm just going to go across the top and then the bottom. Coulombs times newtons times millimeters times seconds squared, meters, and kilometers squared. And on the bottom we have coulombs, kilograms. I'm going to do one more. A newton is a kilogram meter per second squared. So let's do this. Okay. So on the bottom, okay, let's just... Okay, we went across the top. Now going across the bottom, we have coulomb, kilograms, kilometers squared because that's in parentheses, millimeters. This is meters squared because of the parentheses. And then we have newtons and seconds squared, and everything cancels out. And so we actually have just a number here. So first check is good. We're just getting a number. Now the second check, this has to be a number less than 1. So let's put in the numbers. Okay, so 1.6 times 720 times 1.27 times 10 to the 27. So that's all we've got on top. On bottom, 1.67. Here we have 9.55 squared. And let's look at the exponent now. So here we have 10 to the 19. That's up to 22. And 10 to the third would bring it to 10. So wait, we're 19, 22, 28. Because this is actually 10 to the 6th power. So let's take 10 out of here. We can write this as 10 times 10 to the 27th. So that's 10 to the 28th. So again, before moving on, I'm going to check, we check the units. So 1.6, 720, 1.27, 10 to the 27. No other numbers on top. And then 19, 22, and 6, 28, which we wrote that way. So, I'm going to make sure to get this right. So, let's see. 1.6 times 720 times 1.27. So on top, I'm getting 1,000 463.04, not enough to worry about, but why not write it down. And then bottom, 1.67 times 9.55 squared, and then times 10, 1,523. Okay, so we do have a number less than 1. So that's good. Now let's plug in the numbers. I'm getting 0.96. So that's very close to 1. And, sine of 90 degrees is 1. So we should expect 2 theta to be around, so we should expect nearly a 45-degree angle. And, that would be one answer. So we should actually, this is about maximum range. The maximum range occurs when sine of 2 theta equals 1. So we have sine of 2 theta equals 0.96. So we're almost at maximum range. So there should be an angle a little bit less than 45 degrees, and I think a little bit more than 45 degrees, which would give us our answer. But how to find this angle now? Seems simple enough. Take the inverse sine. However, we have to be a little bit careful. When you're dealing with trig functions or the inverses of trig functions, you have to be careful. So I'm going to clear some space on the board. Well, here, we've got this number. .96. So let's get rid of this. And, just let's plot, say, x, sine of x, function looks like this. It just keeps repeating forever. It goes back as well. And when you have something like sine of x equals some number, it looks simple, just take the inverse sine. However, the problem is that this function that I've drawn here does not actually have an inverse. And, that might, of course, inverse sine exists, so, what's going on. Actually, I do want to trace this backwards a little bit as well. So how is it that I say that this does not have an inverse when you know that inverse sine actually does exist? Well, what it means to be a function, if you have like the simplest case, like y equals f of x. The function is a rule where you plug in x and you get y. So if let's look at an example. Say y equals x squared. If I give you x, you know exactly what y is. There's no question about it. If x is 2, then y is 4. And that is a function. There's this rule where you plug in x and you get exactly 1y out of it, and there's no question about what that is. That's a function. Now the inverse function undoes that. And so the question is, let's take this example. If I tell you what x is, you know what y is. If I tell you y equals 4, does that mean that x equals 2? And the answer is not necessarily, because x could be negative 2. Negative 2 squared is 4. And so we have this question, is x 2 or is it negative 2? We have two possible x values for that y. And so this function here is not invertible. If we plot y equals x squared, this function is not invertible. And there's a very nice way to look at these things graphically. This rule that for every x there has to be exactly one y, that's called the vertical line test. See, if I draw a vertical line, every point on that line has the same x value. And so, if it only crosses our function at a maximum of 1 point, then there's no ambiguity there. If I tell you what, if I tell you what x is, this is the only possible y value that it can be. It crosses at 1 point. And so if a graph passes the vertical line test, that means it's a function. Going the other way, though, if I tell you what y is, we look at the horizontal line test. And here we're crossing it at 2 places. And so if I tell you what y is, you don't know what x is. Could be here, could be here. And so in order for a function to be invertible, it has to pass the horizontal line test. So for any horizontal line you draw, you can only cross your graph once. And this clearly fails. If I draw a horizontal line, it actually crosses an infinite number of times. So all the trig functions are not invertible. However, we want to be able to solve equations like this. And so we can make the sine function invertible by restricting the domain. So I'm going to draw this in a different color, just this region here. And I know you've seen this before in math class, but just because you've seen it once doesn't mean you necessarily remember everything. So it's worth going over. So let's say we define sine just between minus pi over 2 and positive pi over 2, or minus 90 degrees and plus 90 degrees. Then this portion, this function, this is a function just with a restricted domain. This function is invertible. And so we can define an inverse for this. This is minus pi over 2. And this is pi over 2. And so this is how we define the inverse sine function. We restrict the domain of sine of x. And so when you get your answer, you're going to get an answer between minus pi over 2 and pi over 2. Let's actually do that. Let's take the inverse sine of 0.96. And I'm in degrees. So it's telling me that 2 theta is equal to 73.7 degrees. So let me just check something. Yeah, I was expecting kind of a smaller value because we're so close to 1, where we would have 90 degrees. But yeah, so taking the inverse sine, it gave us this value right here. Now, just based on the physical problem, we know the actual angle theta has to be in the range of 0 to 90 degrees. We're firing it to the right, so it has to be between 0 and 90 degrees, otherwise it's going backwards. And so 2 theta has to be between 0 and 180 degrees. So we want to look for all the solutions between 0 and 180 degrees. So let's see, this is 90. This is 180 degrees here. So we also want to find this solution. And so we're solving sine of x equals 0.96, and we're looking between 0 and 180 degrees. And so we found one. We found x equals 73.7 degrees. That's one solution. X is 2 theta. So we're just saying sine of x is 0.96. So how do we find this this answer here? That's beyond 90 degrees. I like to look at the unit circle. So if we have a unit circle with a radius of 1, it's not a horrible circle, but kind of off center. It's a little better. So remember, if you look at a point on the unit circle, the y-coordinate is sine. So we have this point here, like this is 1. So like right here, this is 73 degrees. Where like this y-coordinate is 0.96. And so again, we look at, this is a circle. It has perfect symmetry. So the next point we're looking at, the next time, if we keep going around, the next time we're at that y value, this angle has to be equal to that angle. So we could do, or we could say this thing, we could do like 180 minus 73.7. So yeah, like this angle is also 73.7 degrees. Just from here to here, just look at the magnitude of the angle. And so if we go 180 minus 73.7, we'll have x is equal to 106.3 degrees. So let's just check. Adding 0.7, that'd be 107, and then plus 3, 110, plus 7, yeah. So those are the two solutions in this range from 0 to 180 degrees. And x is equal to 2 theta, so our two answers should be, we'll just divide these by 2. But before we do that, let's just double check. I'm going to make sure I'm in degrees and say sine of 73.7, and I'm getting 0.9598, rounding off a little bit, but essentially 0.96. Now let's try sine of 106.3, and I'm getting the exact same thing. So yeah, these are two solutions to this equation. And so if we divide those by 2, we're getting 36.9 degrees. And the other one, well, that would be 53.2. So those are our two angles where we could aim the, this fast-moving proton either at 45 degrees would give us maximum range, so a little bit less than 45, and also a little bit more than 45 will hit that same point, 1.27 millimeters from where it enters this region. So again, kind of a good problem, looking at the actual motion of a charged particle in an electric field. And always good to remind yourself, whenever you have an inverse trig function, you have to be careful. So that was just one problem in chapter 22 on electric fields. Always kind of a good practice. It goes back to some of the earlier things we did, like kinematics, back in the first semester of the sequence. All right, so I think I'll do another problem, but I'll do that in a separate video. So that'll be it for this one.